Imagine a universe governed by the strange rules of quantum mechanics and gravity. Physicists have long used mathematics to explore countless possible universes, each with its own unique properties. These thought experiments have helped unravel mysteries about black holes and the very fabric of reality. But recently, while examining a universe eerily similar to our own, researchers stumbled upon a paradox that challenges our understanding of existence itself. This paradox doesn't just tweak the rules, it shakes the foundations of what we think is possible in the cosmos. Mathematics revealed something astonishing. In this imagined universe, there is only one possible quantum state. That means at its core, this universe is so simple it contains no information, not even the most basic binary choice like a 0 or a 1. This is deeply unsettling because our universe is anything but simple. We see stars, planets, black holes, and life itself all brimming with complexity. Yet in the calculations, none of that richness appears. How can this be? This result stands in stark contrast to what we observe in our universe. The world around us is filled with intricate structures and dynamic processes. From the swirling arms of galaxies to the delicate balance of ecosystems, complexity is everywhere. Yet the math insists that a universe like ours under these assumptions should be utterly featureless. This contradiction is more than a mathematical curiosity, it's a direct challenge to our understanding of reality. Physicists have good reason to trust the calculations. The math is built on solid, well-established physical principles that have been tested time and again. These principles form the backbone of modern physics, guiding our understanding of everything from the tiniest particles to the largest cosmic structures. So when the math leads to such a strange conclusion, it's not something scientists can easily dismiss. The idea that a universe could exist in only one state devoid of all complexity is deeply disturbing. It suggests a world that is nothing like the one we experience, a world without stars, planets, or even the possibility of life. This isn't just a theoretical oddity, it's a profound challenge to our understanding of what a universe can be. How can the math be so right, yet the result so wrong? This paradox led researchers to question a fundamental assumption, that the universe can be described objectively without reference to any observer. In quantum mechanics, the act of observation plays a crucial role. Could it be that a universe without observers is fundamentally incomplete? Perhaps, without someone to witness it, complexity itself loses all meaning. Our daily lives, observation seems simple. We look, we see, we understand. But in the quantum world, observation is far more mysterious. It's not just about seeing, it's about participating in the unfolding of reality. Without observers, the universe described by the math becomes a blank slate stripped of all complexity. This raises a profound question. Does reality require someone to observe it in order to exist in its full richness? One of the greatest challenges in modern physics is uniting quantum mechanics with gravity. These two pillars of science describe the universe at vastly different scales, quantum mechanics for the very small, gravity for the very large. Bridging this gap has led to some of the most exciting and perplexing discoveries in physics, including the paradox we're exploring today. Among the leading approaches to unifying quantum mechanics and gravity is string theory. Instead of point-like particles, string theory envisions the fundamental building blocks of reality as tiny vibrating strings. This elegant idea has the potential to explain everything from the behavior of black holes to the origins of the universe itself. But the mathematics of string theory is notoriously complex, making it a challenging framework to work with. Decades ago, physicists discovered a surprising way to simplify the daunting mathematics of string theory. By considering certain types of universes, they found that everything happening inside spacetime could be described more easily. These simplifications have led to breakthroughs in our understanding of black holes and the flow of information in the universe. Physicists often use thought experiments to push the boundaries of what we know. By imagining different kinds of universes and running the numbers, they can test the limits of physical laws. These mental explorations have already helped solve long-standing puzzles, especially when it comes to black holes and the nature of information. Information is at the heart of many mysteries in physics. In quantum theory, information isn't just about data, it's about the fundamental structure of reality. The paradox of a universe with only one quantum state challenges our understanding of how information is stored, processed, and even created in the cosmos. Black holes are some of the most mysterious objects in the universe. They challenge our understanding of information because anything that falls into a black hole seems to disappear forever. Yet, quantum theory suggests that information can never be truly lost. This tension has driven much of the research into the paradoxes of quantum gravity. If the universe truly requires an observer to be complete, what does that say about our place in the cosmos? Are we simply passive witnesses, or do we play an active role in shaping reality? This question goes beyond physics, touching on philosophy and the very nature of consciousness. Paradox forces us to reconsider the idea of objectivity in science. If the universe cannot be fully described without reference to an observer, then objectivity itself may be an illusion. This challenges centuries of scientific thinking, which has always aimed to describe the world as it is, independent of who is looking. Without observers, the universe described by the math is stripped of all complexity and meaning. Stars, planets, and even life itself become impossible. This suggests that observation is not just a passive act but a creative force that brings complexity into being. Quantum theory allows for a vast landscape of possible universes, each with its own rules and properties. But the paradox shows that not all of these possibilities are equally real. Some may exist only in the abstract world of mathematics, never manifesting as the rich, complex universe we inhabit. Mathematics is a powerful tool for understanding the universe, but it has its limits. The paradox reminds us that math alone may not capture the full richness of reality. Sometimes, the answers we get from equations are only as good as the assumptions we start with. The discovery of this paradox has prompted physicists to revisit some of their most basic assumptions. Is it possible that the universe cannot be fully described without including the observer? If so, what new principles might be needed to explain the complexity we see all around us? As physicists continue to explore the frontiers of quantum theory and gravity, the paradox of the observer-free universe remains a central puzzle. Solving it could lead to new insights about the nature of reality, the role of information, and the fundamental laws that govern the cosmos. The cosmic paradox challenges us to see the universe in a new light. Perhaps reality is not just something we observe, but something we help create. As we continue to probe the mysteries of existence, one thing is clear: the universe is far stranger and more wondrous than we ever imagined.